All right, so today's class 28, sinusoidal forcing. First, just remember that I made a new schedule. I handed it out Friday. It's also posted in Moodle. So today's 4.2, sinusoidal forcing, and then so we skipped 3.7, and test 3 is going to be a take-home instead of an in-class test. And there's actually no class on Friday, May 3rd. We'll just have that day to work on the take-home test. Okay, so first we're going to come back to the problem that we were talking about last class, and we got all caught up in it because it was a little bit tedious with the calculations, and we couldn't remember exactly how to deal with the repeated eigenvalue. So the form of a general solution for a system with real repeated eigenvalues is e to the lambda t v naught plus t e to the lambda t v1, where v naught is the initial condition, x naught, y naught, and v1 is an eigenvector associated with lambda. But it's not just any eigenvector chosen at random, which is what we do when we have two distinct real eigenvalues. We can just choose any one we want. Okay. It's a particular eigenvector such that a minus lambda I times v naught is the one we're looking for. So it kind of makes sense that we're looking for a particular eigenvalue instead of any one that we usually do, because the general form, when we have real distinct eigenvalues, we can use any old eigenvector because you put a constant parameter in front. So it's really the k1 or k2 times your eigenvector. But in the general form, we don't have those parameters, the k1 and the k2, for the repeated eigenvalue. So the parameters show up in the eigenvector itself in the form of x naught and y naught. The initial conditions play the role of the parameters k1 and k2. So here's where this a minus lambda I v naught comes from. So we should have done this in section 3.5. I should have shown it to you. Instead, I just said this is how you get v1. But here's the reason. So we've got linear system, y prime equals a times y, and we're looking for solutions of the form y of t equals e to the lambda t v naught plus t e to the lambda t v1. Okay, and this was motivated, why we were looking for solutions of this form was motivated by an example. So we did one example, we did it out the long way, and it happens to be a well-chosen example where we could get the whole solution by doing some of the little tricky analytic techniques that we have. Separation of variables and then the linearity of an equation. So we were searching for systems that look like this. So what I'm going to do is I'm going to take this equation, this y of t function, and plug it into the differential equation to figure out what v naught and v1 have to be. Well, v naught we know is the initial condition. So if I take y prime here, I get lambda e to the lambda t v naught plus, and then this one I have to do the product rule to take the derivative. So I'm going to have first times the derivative of the second, which would be lambda e to the lambda t v1, plus the second e to the lambda t v1 times the derivative of the first, which is just 1, e to the lambda t v1. So I can do a little bit of combining like terms here, and I've got y prime equals, I have lambda e to the lambda t v1 plus e to the lambda t v1, so that's, oh yes, thank you, that's v naught, yeah. So my terms that have e to the lambda t in them is this term and this term. So I'm just going to factor out e to the lambda t. And I've got lambda v naught plus v1. And then I still have plus t e to the lambda t. This term here, t e to the lambda t times lambda v1. I could, but I didn't.
Okay.
Yeah, and I'm just messing around with it. Yeah, I could. They all have an e to the lambda t in them, but these two have e to the lambda t, and this one's got t e to the lambda t, which makes them somehow different terms. I know, yeah, but lambda is a constant, t is a variable, so I'm thinking of this in terms of combining like terms. Yeah. All right, so there's my y prime, and I have to set that equal. So there's my y prime. That has to equal a times y. So I got to write down a times y here. A times y. A is a matrix. Y is this function here, e to the lambda t v naught plus t e to the lambda t v1. So I can distribute this matrix throughout these parentheses. So I'm going to have e to the lambda t a v naught plus t e to the lambda t a v1. Okay, so this is a times y. This is y prime. They have to be equal to satisfy the differential equation. So set corresponding coefficients equal. So my e to the lambda t term here is a v naught. Over here is lambda v naught plus v1. Solve this guy for v1. And this is where that equation comes from. This is a minus lambda I v naught. And when you set the other two coefficients equal, a v1, the coefficient on t e to the lambda t, has to equal lambda v1 all that tells you is that v1 is an eigenvector. That's the definition of an eigenvector. A v equals lambda v. So we have two conditions on v1. It has to be an eigenvector, and it has to equal a minus lambda I v naught. I knew someone was going to ask me that. It's just a linear algebra thing. So you can't, A is a matrix and lambda is a constant. So when you multiply a matrix times a vector, that works. And a constant times a vector, that works, right? So this looks like you should be able to factor out a v naught, But A minus lambda, that's a matrix minus a constant, doesn't make any sense. So you multiply by the identity matrix I. 28. Yeah, so lambda I, that is the matrix lambda 0, 0, lambda. You can also just find it this way, right? If that makes more sense to you. It comes out the same. A V naught minus lambda V naught. All right, so that's where the V1 comes from. So this is where we were at last class. We said step 1, we want to solve the unforced equation, right? Replace the 6e to the 2t with a 0, and we got a repeated eigenvalue, lambda equals 2. We said, okay, the general form is e to the lambda t v naught plus t e to the lambda t v1. V naught's the initial condition, y naught v naught. And then we calculated v1 the way we were supposed to, and we got the right thing. And then here, some of you knew what you were doing, but I got confused. That is the v1 that goes into the general solution. So this is the general solution to the unforced equation. Replace v naught with the initial condition y naught v naught, and v1 with what you get by doing a minus lambda I v naught. So it's so far we had done everything right. We just didn't get to be able to write that whole thing down. But that's only the general solution to the unforced equation. That's step 1 of 3 when solving the forced equation. So we got that sorted out. Step 2 is to find a particular solution to the forced equation. So our typical guess takes the same form as the forcing function, a e to the 2t. So we try it. We let y be a e to the 2t, and I plugged in here. This is y double prime minus 4y prime plus 4y, using y equals a e to the 2t, and you end up with 0, right? You get 0 equals 6e to the 2t. Bad guess. You can't figure out what a has to be. So I wrote y equals a e to the 2t, just to reiterate what I did here. I took y prime, which is 2a e to the 2t, and y double prime, which would be 4a e to the 2t. And then I plugged into my differential equation. Y double prime minus 4y prime plus 4y. And I'm trying to force this. I want to choose an a that will make this equal 6e to the 2t. And when I plug in, I got 4a e to the 2t minus 4 times 2a e to the 2t plus 4a e to the 2t. And no choice of a will work because the left side always comes out to 0. All my terms cancel. So we say this is a bad guess. So often what we did in chapter 1 when we had to do this guessing technique is when you have a bad guess, it's a reasonable guess to choose a function of the same form as the right-hand side of the equation. But when that doesn't work, we just threw in a t. Anybody remember? You just throw a t. So we would try maybe a t e to the 2t. So this is our second guess. A times t e to the 2t. So we just throw in a t. It also doesn't work. So you're like, oh. I was doing this last night, and I was like, you know, our typical solution for how to deal with the method of undetermined coefficients not working when you have a bad guess is to add a t. Just stick a t in there. And that didn't work either. And I was at a total loss of what to do. So I was like, try it again. Put in another t. A t squared e to the 2t. Multiply by t again. So this is guess 3. And that one works. You plug it in, and a has to be 3. So we have a particular solution. 3t squared e to the 2t. So it's sort of a general good rule of thumb for guessing. If your first guess doesn't work, try to multiply it by t. If that doesn't work, do it again. Multiply by t again. So we have a solution to the unforced equation, the general solution to the unforced equation, and we have a particular solution to the forced equation. We add them together, and we get the general solution to the forced equation. This is general solution to unforced. This is particular solution to forced. Add them together, and you get the general solution to the forced.
So you had it equal to, it was like a y double prime y equal.
The differential equation was that. It's the same thing. It's just that when it's just equal to a number, we would say the forcing function is a constant function. So it'd be like if you have this harmonic oscillator, if you just applied some constant force to it, right? I can't really think of something that would do that. But applying a constant force to it would be, the right-hand side would be a constant. And you'd have to do all the same methods to solve it. That's actually part of your homework. The last 3 problems in your homework deal with constant forcing functions. So that pulls together sort of stuff from last class and stuff that we had skimmed over from section 3.5 that was a poor decision on my part to skim over. Okay, so today's business, sinusoidal forcing. So this type of forcing happens very frequently in systems that model real-world stuff. It can model the shaking of a building in an earthquake or sound waves pushing against a glass. So we're going to use the same methods of yesterday to find a general solution to this equation. So this time, our forcing function is sine of t. So step 1, right, is solve y double prime plus 2y prime plus 2y equals 0. Solve the unforced equation. So what should I do first? Yep, we'll find the eigenvalues by writing down the characteristic equation. You can write it down right from the differential equation. This factors to lambda plus 1. Nope, I gotta use the, it doesn't factor. So lambda is gonna be -2 plus or minus the square root of 4, b squared minus 4 times a times c all over 2a. We're gonna have complex eigenvalues. So I've got -2 plus or minus 4 minus 8, so it's -4, so 2i over 2, which is -1 plus or minus I. So 2 eigenvalues, -1 plus or minus I. So if I want to find the general solution, you can just pick one and find the associated eigenvector, or we learned a shortcut for this in section 3.6, that the solution y of t will always have the form k1 e to the lambda, not lambda, the real part of lambda t cosine omega is the imaginary part of lambda t plus k2. You don't remember this? Well, I never wrote it down like this, but we definitely did it. All right, let's do it the old way.
Well, wait. But if you do that, you still want to pull out the imaginary part so that it's all real, right?
Well, when I write the imaginary part, that's the part that's the coefficient on I. It doesn't include the I.
Oh, it doesn't include that.
Right. Yeah, the imaginary part of a complex number is the coefficient on the I. All right, so let's do the whole thing out. So pick one, say -1 plus I. So y is going to have the form e to the lambda t. Going to distribute this t, so I get e to the -t plus it. Rewrite this as e to the -t times e to the it. And then use Euler's formula on e to the it. So this is going to be e to the -t times cosine t plus I sine t. Distribute the e to the -t, e to the -t cosine t plus I e to the -t sine t. And then we know that we need an eigenvector. Yes, because the general solution is e to the lambda t v, right? Are the solutions. So I need the eigenvector. Let's see.
So you have to write out.
Yeah. So we'll have y prime equals v, v prime equals -2y minus 2v. So my matrix A is 0, 1, -2, -2. And to find my eigenvector, looking for AV equals lambda v. 0, 1, -2, -2 times yv equals -1 plus I times yv. Okay, so 0y plus 1v has to equal -y plus iv. Yes, it's just, yes. Yep, you're absolutely right. Thank you. And then -2y minus 2v equals -v plus iv. These two equations are redundant. One is a multiple of the other. So v is -y plus iy. So let's just pick a value for y, like 1. And then v would have to be -1 plus I. Plus. Y is 1.
Oh, yeah.
So I get -1 plus I times 1. So this is an eigenvector. Okay, -1, sorry, 1, -1 plus I. So I'm just throwing the eigenvector into all of these equations. So y equals e to the negative t cosine t plus. Yeah, I meant to do that. And then my eigenvector is 1, negative 1 plus I. I'm really only interested in the solution, in the scalar solution y of t. I don't really care what v of t is. Yeah. So now I don't even have to, look at that part. I can just use the 1 here. Because this is a vector valued function that has y, it's giving me y and v as the two components. So this is a vector valued solution. I really am only interested in a scalar solution. What's y of t? What is my function y of t? Yes. Yes, that's the shortcut that I started writing down, but this way you'll see where it comes from, or you'll be reminded where it comes from. So y of t is going to be e to the negative t cosine t plus I e to the negative t sine t. So yeah, we didn't really need to do the eigenvector thing for if we only want the scalar solution. And actually, even if you want the vector valued solution, once you have the scalar one, you can just take its derivative and you have v of t also. So this, remember, gives us two solutions. This is a particular solution, but the real part and the imaginary part are both solutions in their own right. So we take a linear combination of them, and the general solution to the homogeneous equation is going to be k1 e to the negative t cosine t plus k2 e to the negative t sine t. So I took the real part and the imaginary part, take a linear combination of the two. So what I started saying is that if your eigenvalue, remember lambda was negative 1 plus I, the negative 1 shows up in the exponents on E, and the 1, the imaginary part, the coefficient on the I, shows up here. Right. So you can just jump from the eigenvalue to the scalar solution without having to do all that complex arithmetic. And then just take the derivative to get v. Yeah. All right, so that's step 1, right? We got the general solution to the forced equation, to the unforced equation. Sorry. All right, so step 1, okay, good. Step 2. Now we have to find a particular solution to the forced equation. I think that's the original equation. Yeah. So we need a guess. Yes, it's a good choice to try to pick your guess to have the same form as the forcing function. So if we try this, y double prime is going to be negative alpha cosine t, negative alpha sine t, plus 2 alpha cosine t, plus 2 alpha sine t, and we want to make that equal 1 sine t. Yeah, because it introduces, no matter which one you choose, if you choose alpha sine or alpha cosine, It's going to introduce the other trig function into your equation. Okay, let's try. Y equals alpha cosine t. So y double prime, that would be negative alpha sine, negative alpha cosine, and then plus 2 times the derivative, which would be negative alpha sine t, negative, and then plus 2y, 2 alpha cosine, no, because I have a negative alpha and a plus 2 alpha, so they don't cancel. So you're left with 1 cosine minus 2 alpha sine. So maybe both. Let's try y equals alpha cosine t plus beta sine t. A linear combination of the two sinusoidal functions. Okay, so y double prime. Well, alpha cosine y double prime we said was negative alpha cosine plus 2 times y. Oh, I forgot to do the plus the beta sine. So the derivative of beta sine would be beta cosine, negative beta cosine, no sine, negative beta sine. Then plus 2 times y prime. So that's going to be negative alpha sine plus beta cosine. And then plus 2 times y. And we're trying to force all this to equal sine t. So distribute combine like terms. Cosine t is I have a negative alpha plus 2 beta plus 2 alpha, right? Negative alpha plus 2 beta plus 2 alpha. So alpha plus 2 beta. Just combining like terms. So I have negative alpha cosine t, then plus 2 beta cosine t, plus 2 alpha cosine t. All right, so now I'm going to distribute and combine like terms for my sines. I have negative beta sine minus 2 alpha sine plus 2 beta sine. So I'm going to have beta minus 2 alpha sine. And I want this to equal 0 cosine t plus 1 sine t. That's an alpha, yeah. Yeah, I know. So you said the coefficient's equal, yeah. So alpha plus 2 beta has to be 0, and beta minus 2 alpha has to be 1. So 5, did I mess up? Okay. So alpha is negative 2/5, and beta is 1 plus 2 times negative 2/5. 1 minus 4/5 is 1/5. Mm-hmm. Is that far enough? So we have a particular solution. Negative 2/5 cosine t plus 1/5 sine t. Okay, that's step 2.
So one of these problems.
Once you've done it a couple times, it doesn't feel as long. Sorry.
No rare here.
Yeah, so now you just add the two solutions that we have together. The general solution to the unforced plus the particular solution to the forced, and we get the general solution to the forced equation. Sure, yep. All right, so then the very last step is to add. We're looking for y general. That is y sub h plus y particular. So this is the general solution to the forced equation is equal to the general solution to the unforced equation, which was k1 e to the negative t sine t cosine t plus k2 e to the negative t sine t. And then add the particular solution we just found, which was negative 2/5 cosine t plus 1/5 sine t. So there's our general solution.
We were talking about like one of those problems where you have defined solution. You take a derivative of it.
Yeah, you just treat I like a constant. Yeah. So far, we haven't really done anything new today, except change the type of forcing function on the right. And all that forced us to do was think about what kind of guess we were going to need to use. So what is new today is that we're going to develop another technique for finding the general solution to this equation, to an equation with sinusoidal forcing. So the technique is going to come in handy later. So even though it's not strictly necessary now, because we can do it by using an appropriate guess, alpha cosine plus beta sine. So it's not really necessary now, but it's a good time to introduce it. Okay, so we're just going to solve the same equation we did before, but using a different technique. So here's the technique. Over here, this is going to seem random at first, okay? But it's going to lead us to like, oh, that's pretty handy. In this differential equation, replace the sine t with an e to the it. So we're going to have y double prime plus 2y prime plus 2y equals e to the it. Now, those aren't exactly equivalent equations, right? Sine t does not equal e to the it. But e to the it has a sine t in it, right? If I expand e to the it, it's cosine t plus I sine t. Okay, so it's related to the original differential equation, but not the same. So the reason I like this, though, the reason we kind of like replacing sine t with e to the it is you know how to guess for an exponential. You just choose a e to the same exponent as in the original equation. So I would like to solve this one instead because the right-hand side is an exponential, which I know how to work with. So the question is, though, because this equation is related to this equation, the solution to this equation should be related to this equation. The question is how. So I'm just going to play around with this guy a little bit until I figure out how the solutions are related. All right, so guess a solution. Y equals a e to the it, or alpha e to the it. Yes. So then the right-hand side would be a constant forcing function. Yeah. It'll still work. All right, so if this is my guess, a e to the it, I'm going to plug in my y double prime, my y prime, and my y, and try to make them equal. So y double prime here would be a e to the it times I would be y prime. So let's just write them all down here. And then y double prime would be ai e to the it times I again, but the I times the I makes -1. So this is going to be negative a e to the it. So then I'm going to plug into this differential equation. I guess I'll write over here. I didn't want to, but negative a e to the it, that's y double prime, plus 2y prime is 2ai e to the it, plus 2y, 2a e to the it, making this equal e to the it. So every term has an e to the it, so I'm just going to sort of combine them all into one. So I have e to the it times negative a plus 2a gives me an a plus 2ai. So I'm just factoring out an e to the it, or combining like terms. So then set your coefficients equal. This has to equal 1. Solve for a. And you get a has to be 1 over 1 plus 2i. So I have a function, right? My guess, plug in my a into my guess, and now I have a function that makes this equation with the forcing function e to the it true. So y equals a e to the it, and this is my a. One over 1 plus 2i, a e to the it. So that's a particular solution. Right, but not to the forcing function that I want, but a related one. Okay, apply Euler's formula to e to the it here. And remember that this function y, it's a solution to the forcing function e to the it, but also the real part and the imaginary part are both solutions. And one of them will be a solution to the forcing function we're looking for. And I should have done something else before I derived this. Got it. All right, so more in general here. I've got y double prime plus 2y prime. I have some complex solution, which I already found, right? We'll call it yc for y complex. And it's got a real part plus I times an imaginary part. And we already know what those are. We already figured all this out, but I should have done this first. Okay. And I know that I can write this as cosine t plus I sine t. Y real plus y complex. There is some solution to this equation, some complex valued function that solves this equation. And it's a real plus an imaginary, real part plus an imaginary part. No, let's leave that off for now. You'll see where it comes from in a minute. Okay, so now plugging my complex equation into the differential equation, I get y, oh my goodness, this class is going too fast. Y double prime plus 2 y prime plus 2y has to equal e to the it. And so this is going to be, when you take the derivative of the complex, you just take the derivative of each part. Same old derivative rules as always. The real part plus so that's y double prime plus 2 times y prime y double prime plus 2y prime plus 2y and rewrite e to the it as cosine t plus I sine t. This says RE for real. Oh, these are all C's. Yeah, these are all C's. Sorry. I'm just plugging this complex valued solution into the differential equation. All right, collect all your real parts. Y real double prime plus 2y real prime plus 2y real has to equal cosine t. And match up your imaginary parts, and you're going to have y imaginary double prime plus 2y imaginary prime plus 2y imaginary has to equal sine t. And I left the i's off of everything because I'm just like dividing them out. There's an I on every term on both sides. So one of these two equations is our original differential equation with the correct forcing function. Which one is it? The one with the sign. This is the original forcing equation. So if I just take the imaginary part from the complex valued forcing function, I'll have solved my original problem.
How did you know it was e to the I?
Yeah. No, I just, because it was sine t. So if it was sine 2t, I would have used e to the I 2t, right? Whatever the argument is on your original forcing function, do e to the I times that argument. If it's cos, same thing. Except in that case, you'll take the real part of the complex valued solution, right? Because, yeah, yep. But then the solution would be the real part of the complex. 2 minutes, I can finish. Okay, so where was I? Here's my solution to the incorrect forcing function. But if I just grab the imaginary part of that, that's the solution. That's a particular solution to my forcing, the correct forcing function. Oh, I didn't finish. Yeah, I still have eyes because I didn't finish. I just have to distribute. Yeah, and some of them are going to cancel out. I'm almost. Oh, it's only 35. Okay, good. I thought the little hand was the minute hand. All right, we're good. We're good. Okay. Okay, so distribute. Y equals cosine t over 1 plus 2I plus I over 1 plus 2I sine t. Let's make this I sine t. Okay, so I want to make this look like a plus bi. I want to put it in the form of like a standard complex number so that I can grab the imaginary part. So when you divide complex numbers, multiply by the top and bottom by the conjugate. All right, so now we have cosine t minus 2I cosine t over. When I FOIL these, I get 1, those cancel, minus 4I squared, so I get 5 as my denominator. Plus I sine t minus 2I squared sine t, which is really plus 2 sine t over 5. Yep, I can add the tops because my denominators are the same, and I'm going to collect real parts and imaginary parts. So my real part is cosine t plus 2 sine t. I don't think so. Because it's minus 2I squared, and the I squared changes the sign. Cosine t plus 2 sine t over 5 plus negative 2 cosine t plus sine t over 5 times I. Okay, so now just take the imaginary part. Yep, that's what it is. So this is my real solution, my solution to the forcing function sine t. So this is the one I'm looking for. -2/5 cosine t plus 1/5 sine t. No, because that was just the particular solution. That was just the particular solution. So the k's come from finding the unforced. Yeah, the k's come from the unforced. So this is just another way of finding y particular. So this is another way to do step 2. Step 1 stays the same. Yes. Yes, that's what we're going to talk about. And this is the same thing we got, right, for y particular when we did it just with a guessing. Yeah. So it's kind of fun. Another way to do it. So here's several solutions. Sorry, Matt. You can take your time. Go ahead. All right. So here's several solutions to the ODE plotted. The forced equation has this general solution, right? We found this. This is the first thing we did today. We found this general solution. The first two terms, because of the e to the negative t, go away, right? As t gets large, they tend to 0, leaving you with just the steady state sinusoidal solution, -2/5 cosine t plus 1/5 sine t. That's just the particular solution. So wouldn't it be nice if we could know the amplitude and period of that sinusoidal function? Right? It clearly, is just a sinusoidal function. It's got some amplitude and period. So what we would like to do is write this as a single trig function, typically cosine. I want to just write this as cosine with a cosine of some stuff. All right, so you can do this with trig identities. Okay, so you could just manipulate the heck out of that thing until you get it to be cosine of just some stuff. So you could use trig identities. A little bit of a quicker way is to use the complex solution and change it to polar form. Quicker. You got to remember how to do those things, but it is quicker. So remember, that was our complex solution, a e to the it, and we found an a, right? And this was 1 minus 2y over 5. So that's just, I'm just converting cosine t plus, from way back here. Earlier. And then the 5 came in because when I got rid of the i's in the denominators, right? So I'm just converting this to a e to the it, or whatever. All right, so this is my a. It's a complex number. 1/5 minus 2/5 I. So when you distribute out that e to the it and then change it to cosine t plus I sine t, you're going to get the equation of our solution. Okay, so there it is in complex form. I want to change it to polar form. So remember, you can take a complex number, 1/5 minus 2/5 I, and you can graph it. We have the real axis and the imaginary axis. So you go over 1/5, down 2/5. All right, so now we want to change this point to its polar form. And its polar form, we want to write that complex number A as RE to the I theta. R is the distance from the origin. Theta is the angle made with the x-axis. With the real axis, yes, thank you. No, all we have to do is treat this as a right triangle and find this angle theta. You don't. Yes, if I want. Yes, I would find that and say it's either negative, or I'd go all the way around to find theta. Yeah. Yeah, and it would be that would be a different point. Yeah. For our purposes, it's not going to matter. We just need to find, because the trig functions are periodic. It's going to end up just working out fine if you just find that acute angle. All right, so R, this is 0.4. Let me enlarge this triangle here. That's what we're looking for. Use the Pythagorean theorem to get R, and theta will be the arctan of 0.4 over 0.2. The inverse tangent of 0.4 over 0.2, which is 2. Oh, the sign does matter. And the way you deal with it is that this is just put a negative 0.4 because it's down. And so this is the arctan of -2. All right, so then R ends up being 1 over √5. And theta ends up being about -63 degrees. Nope. Because this is differential equations are most frequently used by physicists. So no, physicists like degrees. So A ends up being 1 over √5 times e to the -63 degrees I. But my complex valued solution was A e to the IT. And I just figured out a new way to express A. Okay, so now add the exponents. No, but they're like terms. So you get negative 63 degrees plus t times I. Change it to use Euler's formula here. 1 over root 5 times cosine t minus 63 degrees plus I sine t minus 63 degrees. When you add these two? No, it's like terms. Yeah, so it's just negative 63I plus IT and then factor out the I. All right, and then remember that our particular solution was just the imaginary part of the a e to the it. So all I need is the sine. So the thing I'm looking for is just sine of t minus 63 degrees. So I've written it as a single trig function, so that was my first goal. And I now know its amplitude would be 1 and its period would be 2 pi over 1, the coefficient on the t. So I know it's a sine function, amplitude and period, amplitude 1, period 2 pi. Oh, I forgot to distribute that. Yeah. Thank you. So the amplitude is 1 over square root of 5. Period is 2 pi. But traditionally, we like to use cosine, of course, because we got sine. So we just use that cosine of an angle, any angle, is sine of 90 minus the angle, because cofunctions of complementary angles are the same. So almost done, times the cosine of t minus 60. So I have to do 90 minus all of that. Or do I do that minus 90 minus 153? So I get 153 minus t. Done. Whew. All right, we'll talk about it a little more next class.